So, Ratamar, with a recap of what we did last time, ne? I gotta know Kishirile the screen that says electricity. What are you seeing on your screen now? Magdalene?
Emoji electricity, recap, voltage, current resistance, and
Okay. Yeah, so Rotumila discussion, I think this was as far back as grade 10. So I'll just make that note. So this is like up to grade 10. Oh, yeah, like it's shown there. Ne? And then we introduced the concept of voltage, which is the electromotive force that moves electrons throughout the conductor in a circuit. We discussed current, which is the flow of charge or the flow of those charged electrons in a conductor, and a resistance being a sort of stumbling block to the flow of those charges, which that kinetic energy when it's slowed, when the charges electric king when the charges in the conductor are slowed down by whatever the resistance is made of, that produces heat, and then we can measure that. And then we discussed circuits. We did resistors in series and parallel, voltage for both circuits in series and parallel, and we also did calculations for circuits in series and parallel. Then moving on to grade 11, we expanded a bit on Ohm's law and discussed it for ohmic and non-ohmic resistors. Ne? So for grade 11, we did Ohm's law in a series circuit. We also did ohmic resistors in a series circuit. Then we looked at ohmic resistors in series, where the current flow first passes one resistor, then the other, and we could identify the voltage drop. Then we looked at parallel resistors. And in parallel, we looked at the types of calculations of parallel circuits where resistors are in parallel. Then, let me just do this, yeah. 5, 6, 7. Yes. Okay, so slide 7. All right. Then ohmic resistors in parallel, we did some calculations on that, where we had to find the current passing through the one resistor in parallel and the other resistor in parallel. Then we discussed a little equivalent resistance, where if you have resistors in parallel as part of a circuit, you can equate those to one resistor, and that would be an equivalent resistance. So this, you still apply the same calculations that you've learned for parallel resistors. So our discussion last time, I believe last week, be power and energy, where we talked about how power is measured in watts and energy is measured in joules. The difference between them being power is how rapidly work is done, and it's the work done per unit time. So that rapidly refers to a sense of time, whereas energy is that which is used to do work on the electrons. The definitions are still similar to jam mechanics, when you think about work being done on electrons that are moving in a conductor. Um, then the definition of electric power was simply, are we still together?
Yeah, ne khatile mara ke dile so.
Okay, it's fine. Definition ya power, electrical power, which is that power that you see more microwaving or on your heater or speaker. Ne? It is simply the product of current and voltage. Ne? So again, the definition is how rapidly work is done. So we can write power in two other ways. The first one being as the square of current times the resistance. The second one being as the square of voltage divided by resistance. And that's simply if you take Ohm's law and you substitute, if you make the voltage the subject of the formula, then you will substitute it here and you will get I times R, and that gives you IR squared. And if you make current the subject of the formula and you substitute it into the original equation here, power, electrical power, then you get V times V divided by R. So the first calculation we did for grade 11 was where we are given the voltage of 5 volts in a circuit and a resistance of 2 ohms. Yes, that's the example I actually have in front of me. So when we calculate the electrical power, we found that if we use the other formula for electrical power being V squared over R, because we have those terms V and R, then we get that amount of power in the circuit. And then in another example of calculating electrical power, this time we're given the current and the resistance. So we could then work out the electrical power in the circuit. Right? So that would be the electrical power of the resistor rather in the circuit. Yes, that's the correct way to use the English. The other example we looked at was for electric power in a series circuit. And this time we were given the resistance of one resistor. The other resistor were not given its resistance value, but we are given the current in the circuit and the voltage in the circuit. And we first had to find both the resistance of R2 and the electric power in R2. So we first started by looking at the total resistance, which we could calculate by dividing the total voltage which is given by the current in the system, and that gave us 24 volts, which equals the total resistance, which is these two added up. And we could then do additive inverses, and we got the answer for the resistance in R2. And then using the formula for electric power, the one with the square of current times resistance, we could then find the power in the resistor that we used to not know before. Okay. So yes, Raffaele Chimoki, and then we said we will continue from that chapter. So I'm just gonna switch sharing that screen and share this screen because it's all up from mall, ne? Kindly give me a moment. I just want to blow my nose. Right. Yes. So today's problems, ne? Re tlo thoma ka ya electricity, ne? So grades 10 to 12. So Nale a worked example on page 403 of Siavula Learning Guide, and it's a circuit that has a battery, and in the circuit we've got two parallel circuits in that circuit. So we've got 4 resistors in total, but each pair of resistors is configured. Do you know what the word configure means? Yeah, Magdalene. Why is this not showing there? Oh no. Oh no. Oh no. I wonder which one am I showing? Oh, there we go. Okay. Yeah. Can you see the circuit now? You can do a thumbs up, ne? Can you see the circuit?
Kidra.
Obana circuit on your screen. I'm sharing screen, ne? All right. Thanks for that. All right. So we've got 2 parallel resistors forming a parallel circuit 1. So I'm just going to use different colors for each parallel circuit, ne? And then we're going to use this color coding to work out the equivalent resistors, ne? Right, so we'll call this R1, this one R2, this is R3, and this is R4. Alright, so this we'll call parallel circuit 1. So the equivalent resistance would be resistance for parallel circuit 1. Or rather, let me write it in a yellow color. to show that it corresponds with that. So it's R parallel 1, and this one, which is red, will be R parallel 2. Ne? We are also given that the current leaving the battery is 1,07 amps, and the total power dissipated in the circuit is 6.42 watt. So we'll just write P subscript total there. Ne? Now, the resistance of the parallel circuit, 1, 2, the ratio of the resistance of the parallel circuit, 1, to the ratio to the resistance of the parallel circuit, 2, is 1:2. Ne? So in other words, whatever the equivalent resistance is for the yellow circuit, um, the red circuit is twice that resistance. Do you understand that part? Or na e tlhalosa gore? Magdalene, is that part clear, or should we explain it further? So I just mentioned this part here, ne, where the equivalent resistance of this parallel circuit to the equivalent resistance of this parallel circuit. In other words, whatever value this equivalent resistance is, then this value is 2 times that resistance value. So in other words, if the equivalent resistance here, let's say we work it out, and then it's 3 ohms, then this would be 6 ohms. Do you get that?
Yeah, I
You understand that, no?
now get.
Eh? Kira, do you understand it?
Yeah, no, so okay, understand.
Okay. And then the other piece of information that we are given, it's that the resistance of R1 to R2. So in other words, the ratio of these two resistances, R1 and R2, is 3:5. So in other words, um, mm, let's see. So if the resistance in R1, for example, is, let's say it's 30 ohms, then this would be 50 ohms. So the ratio of proportion, the ratio rather of these two is 3:5. Ne? And we're also given that R3 is 7 ohms. So we have to use all of this information to find all of these resistances in the circuit, as well as the other information. So for now, we are asked to find, number 1, the voltage in the battery. So let me just write it in full: voltage. So we have to find the voltage in the battery. So in other words, we'll call that V battery or V total. Ne? What we do know, that's the first thing that we have to find. Then the second thing that we have to find is the power that is dissipated. Do you understand what the word dissipate means? Maggie? You don't know what that word means. Okay, let's quickly look it up. So to dissipate is to break apart, ne? Or attenuate to the point of disappearing. Attenuate is like to arrest. So in some engineering, I know in hydraulic engineering, there are things called attenuation ponds. So salo bona ka thoko tsa ditsela tse dingwe ne, there will be like a road. Let's say ke skontiri so, ne? There's the skontiri. Then ka thoko tsa tsela go na le V drain e so. V drain ya gona ke ya concrete. A seng go bona ntwe so. No? Yes? Azangwa. Maybe that's not the best example. Think of one. Okay, Blood River wa tseba ke. Mola mo dikoloi di fetang bridge bola. Sharp. So how lebella, like, let's say we are motoring from zone 4, ne? From busy corner side. You're traveling direction in ya Moleji side, ne? O feta Blood River. Mole ka you safe. So come on writing out o bona ntho keteng ke leboto so a ke re nokele ya feta so, and then o bona ntho keteng ke leboto ka mo thoko tsa yona. Yeah, so that thing ne ga metsi a tlala salo I bona when it's flooded. Yeah, so when it's flooded, that water moves at such a high energy. So kamopeli kamole on the downside of it. So let's say kilowatt relay so ne. Let's say that wall. When like on it's a bit dry, so mitiale are somewhere leveling eki. Hawon? Agamra water lay. But Ramitial atala I have leveling yagodim adia so ne. So then it's flooded. So that energy, kinetic energy, ne, it's so much that Ramitial awela fast so the energy is too much. What it does is it erodes the floor here, ne? So to prevent that erosion, you have to arrest the flow. You have to slow down the flow or break it apart or scatter it, ne? So ranchi the structure tsa mkhuto di tla ba le di attenuation pond. So like a pond, like a damo lenyane, so that metsi a be slow as ka move ka lebelo le lentši with too much speed. Maybe if someone who's a dam engineer would probably find fault in how I'm trying to explain this, because I'm not a dam engineer, but the idea e ke nyaka go bontsha yona about what the word dissipate means ke ntho ya gore things like body blood river ne, those structures they are designed so that metsi a ska ba le lebelo le lentši and then mo metsi a fetago gona a be a senya lefase. That's the whole point. So dissipate is to break apart or to cause to vanish or to squander. So in other words, to fokotša maatla a that power, yeah, that metsi. So in the same way, we have to think about dissipate here. Ne? So that's what we're going to calculate in the second part of the calculation. And then the third thing we have to find is the value of each resistor and R1, R2, and R4. So we have to find R1, R2, and R4, as well as we have to find the power dissipated by R1, the power dissipated by R2, the power dissipated by R3, and the power dissipated by R4. Ne? So that's what we have to find. So this thing, we have to start first with the voltage in the battery. Ne? Now, we have gathered all the information that we possibly could find that is given, and what is given is the current as well as the total power that is dissipated in the circuit. In other words, the power that is broken apart in the whole circuit. Obviously, that power is dissipated by these resistors, but in total, it's 6.42. It's not 6.42 for this or that or that or that. It's 6.42 in the entire system. So we can use that power, 6.42 again, watts. So we can use that power to our advantage. We are also given the current in the system, and we know that it is 1,07 amps. Ne? So now that we have this information, we know that P is equal to V times I, and that's a definition for power. So given that, we can substitute. So 6,42 watts will equal, we don't know what the voltage is in the battery, but we do know the current in the circuit, and it's 1,07 amps. Then we can take the multiplicative inverse of the current and solve for the voltage. That one is straightforward, one. Can you see? It's a pretty straightforward calculation, eh? Can you see that? Hello? All right. So then we take the multiplicative inverse. Then we find that V, voltage in the battery, it equals how much? What is 6.42 divided by 1,07? 6.42 divided by 1, 0. Okay. It's 6, ne? Over 6 is square. All right, so it gives us a square 6. Okay. Well, in the circuit, I put a yellow circle around RP1. Remember, a yellow enclosure. and a red enclosure there. So we're going to do that so that in the next, again, we want to simplify our problem. We're going to redraw the circuit again, in part 2. We're going to redraw the circuit. So let's redraw the circuit. But this time, instead of resistor J4, we'll just draw the same resistors that we have, but let's draw them in the colors that we gave them initially. I carry earlier RP1 refill yellow color, and then RP2 refer red color. So let's carry on with that convention. Convention is an agreement, ne? So we carry on with that convention which we gave ourselves. So what we agreed upon initially is that RP1 is yellow and RP2 is red. Ne? So we need to first find the power dissipated in the equivalent resistors. Ne? So let's try and work with that. Firstly, remember Ohm's law. Ne? That's our triangle, Ohm's law. Ne? So from Ohm's law, we know that that's the case. Then we also know that we've got, for this circuit, then the resistance total will be RP1 plus RP2, ne? And it must equal the total voltage in the battery divided by the total current in the circuit, ne? And this will be the total resistance. So we know the total voltage, which is 6 volts. And we also know the current, which is 1,07 amps. And what does that give us for our total resistance? It means we must take 6 and divide it by 1,07. Now we must note that we are not really repeating things here, but we are simply taking advantage of the fact that the whole circuit as we know it, in a voltage that is given, or rather that is calculated, and in a current that is given. So we're just simply using that information to our advantage. So riketoshe 0.07 0.61. All right. So far, are we still together? Okay. So now we have to recall an important piece of information. RP1, so the resistance equivalent of parallel circuit 1 is half the resistance of parallel circuit 2. So in other words, the split between must be so that the red one is 2 times the yellow one, like it was given in our initial statement, problem statement. And what we know from this, is that RP1 plus RP2 must equal R total, which we've calculated here. Ne? So this R total must equal RP2 plus RP1, which we are given there. And now we also know that RP1 is half of RP2. Therefore, R total must equal RP1 plus a half times RP no. RP2 plus a half times RP2. Yes, that's what I want to say. Yeah, because if RP1 is half of RP2, then when I substitute that there, it should look like this. Yes. That means 3 over 2 RP2 R total. Then if we solve for RP2, that's going to equal 2/3 of R total, which is 2/3 of 5,61, which is, so this times 2 over 3, it will gonna be 3,74 ohms, and that means then the balance then therefore, let's just make a new slide. Therefore, RP1, which is a half of RP2, will be half times 3,74 ohms, and that is, so this times 0.5, 1,87 ohms. So I just want to see this plus 3.74. Okay, so it checks out. Ne? Yeah, ask.
R total is equals to RP squared plus half RP1 plus half RP squared as sharp.
Or rather, this part here. This part here.
Okay, yeah, calculation now. Yeah, part here.
That part, okay. Now let me explain it. Ne? I just wanna quickly 1.87 ohms plus 3.74, and that equals 5,61 ohms, which is correct. Okay, cool. So let me explain. Ne? Right. So agree circuit arena had 4 resistors initially, but now we simplify it to equivalent resistances. Ne? That part where we simplify. You can just do a thumbs up so that we can pila because in a short while I'll just need to change the call. All right, sharp. So RP1, RP2. Now, we're told that the ratio of RP1 to RP2 is 1:2. That part I hope all again. Okay, I'm just gonna switch to the next screen so that you can see where I'm talking about. All right, so so it's good that we're hopola. Now I get the part here how we got the total resistance. You understand it, I get. Okay, sharp. So we got R total and it equals 5,61 ohms. This R total is the same as RP1 plus RP2. Ne? That one, ya kwagala here. Sharp. But now, how these two, let's say ke a bar ya R total, ne? So the ratio, if we have R total and it's divided 3 ways, ne? It means 2 of these portions, ne, must be allocated to RP1 and 1 of these portions must be allocated to RP1. So 2 of these should be allocated to RP2 and 1 of these portions must be allocated to RP1. So does it start to look clear? Okay, so we're going to do the math to find how this is divided. Now, in doing the math, we have to say, okay, if RP1 is half of RP2, ne? Because remember, it takes king. So two, yeah. So that means if RP2 is 2 times RP1, then it means RP1. If RP2 is twice that, then it means this is half of that. So is it still? Okay, so if this is twice that, then that is half of that. And that is the substitution we're going to make here. So we're going to say RP1 is half of RP2 because we want to have one that we can solve for RP2. Because once we've solved for one of them, then we've got the other one. So, and that's all we did here. So I'll just put here RP2. But then the yellow one, we now convert it to, because we've written it in terms of RP2. So it's half of RP2. So now we end up having 1.5 times RP2, 5,61 ohms. Then when we solve for RP2, 2/3 of the total resistance. And that gives us 3,74 ohms. So it clarifies everything. Eh? That's great. That's great. That's great. Then RP1 will then become 1,87 ohms. Okay, so now we found the equivalent resistance of parallel circuit 1 and the equivalent resistance of parallel circuit 2. So 1,87 ohms and 3,74 ohms. Now remember, the sum of these two should give us the total resistance, but it's given us the total resistance. So this is 1,87 ohms, and this part here is 3,74 ohms. The total resistance is 5,61 ohms. When we visualize it, we can also make sense of it practically. So we've just done that. Now, we're going to go. Can I just ask for 2 minutes to set up a new call? Because this one is going to cut shortly. So I don't want it to cut whilst I'm in the middle of explaining nicely. Ne? So just 2 minutes, you can quickly leave the call and then I'll send you an invite to our new call. Ne? Sharp. Sorry. Start instant meeting. Now listen to me, brother. Now listen to me. I don't want to anymore. Mm, 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 mm. Okay, that's great. That's good. That's good. That's good.
Thank you.
All right, so we were now moving to the next part of the problem. Ne? Now we found the equivalent resistances. So now we can find the power dissipated So in other words, the power that has been we said dissipate is to break apart. The power that's been broken apart by the equivalent resistances. Ne? So we're going to do just that. So power is defined as current squared times resistance. Ne? So we'll do the same for P1, equivalent resistance P1 or parallel circuit 1. And we'll also do the same for the power dissipated by the equivalent resistance of parallel circuit 2. Ne? Now what happens is we've got the current in the circuit, and remember, because our circuit, we visualize it as these parallel configurations, they are equivalent resistances in series. Ne? So because they're in series, the current remains the same throughout. So that doesn't change. It's 1,07. We square it. We found the equivalent resistance of parallel circuit 1 to be 1,87 ohms. And we are going to use the same value for current, square it, and then work out, or rather substitute, the equivalent resistance there. So for the first one, the first parallel circuit gives us a power of 2.14 watt, and then the second one gives us 4.28 watt. This calculation is straightforward. Yeah? All right. Okay. So now we found the power rating ke bokae for the equivalent resistances, but that's not for each of the resistances. But we can use the equivalent resistances, these ones, to work out the individual resistances R1, R2, R and R4, because on R3, we've got R3. So I'm just going to redraw the circuit so that it reminds us where we come from. So we come from here. Ne? We come from here. Ne? So there's R1, there's R2. R3 was given as how much again? It was given as was it 3 ohms? 7 ohms. Yes, 7 ohms. R3 was given as 7 ohms. And we also don't know R4. Yeah? But we do know that for the yellow configuration, which is RP1, resistance of parallel configuration 1, it must equal 1 over R1 plus 1 over R2. And in the same way, 1 over RP2 must equal 1 over R3 plus 1 over R4. Luckily, we do know R3 because it's given as 7. So we'll have 1 over 7 ohms plus 1 over R4 equals 1 over RP2 is 3.74. Now from this, we can solve for from this we can solve for R4. We can solve for R4. So let's just do this. Okay, I'm gonna need to make a division there, like that. And I also need to color this one in. Yeah. And Magdalene, before you get to Olapili, this part you understand how it's used, Mas. Where, Magdalene?
Huh?
This part here, the equivalent resistance of parallel circuit 2 equals 1 over R3 plus 1 over R4. You understand where this comes from, Mas?
Yeah, okay, one and so.
Yes, get that theory or when resistors are in parallel, the total resistance, the individual resistances, they become smaller. You remember that?
Yeah.
Yes. So we are just going to solve for R4 using that. So in other words, 1 divided by 3,74 minus 1 over 7, gonna 1 over R4. Here we can have 7 times 3,74. So that goes in there 7 times 4 equals 1 over R4. Then this should be, let's see, 7 minus 3,74 divide by 7 times 3,74. So this equals 0.125 1 over R4. Therefore R4 I just need to invert that. 8.03 ohms. Ne? So we found that 8.03 ohms. That's R4. So we found R4. We can use, remember the problem is given that the ratio of resistance 1 to resistance 3, sorry, to resistor 2 is 3:5. Remember that. R1 to R2 is 3:5. So we need to remind ourselves that. So 1 over RP1 equals 1 over R1 plus 1 over R2. And R1 to R2 is 3 is to 5. Okay, so now we're going to do that. And what are we going to do with that information? That means for every, let's see. So this means R1 over R2 equals 3 over 5, or R2 over R1 equals 5 over 3. Okay? So let's see. Okay. Can you see what's going on here? Sorry, let me just change the slide. Yeah. So, okay. Ne? Popular in maths when we're doing similar triangles. Sometimes you'll find that you can express the one ratio like this, but you can also express it like this or like that. Either or, regardless of which one is the unknown between the two, whether you write the ratio like this or like that, you'll still be able to find the other that you don't know. You know, must this are what ratios, ne? Yes? No? Let's not make sure. Okay, great. So, we're gonna go with this one here because it's close enough to that. We're gonna go with this one because it's close enough to that. And how are we going to do it? We are going to say that we are going to say that this equals, so if we make R2 subject of the formula, then R2 is 5 times R1 over 3. Ne? And we're going to substitute that into this equation. So we'll have 1 over 5 R1 over 3 plus 1 over R1 equals 1 over RP1. And this one is a number divided by a fraction, so it's the same as the fraction inverted. So we rewrite like that. And then we can add over here 1 over RP1. So R1 goes in here 5 times. 5 times 1 is 1. And that goes in there once, and 1 times that is 3. So now we've got 8 over 5 R1 equals 1 over RP1. But let's substitute. That is 1,87, I believe. And we can do multiplicative inverses. So R1 will equal 8 times 1.87 over 5, and that gives us 8 times 1.87 divided by 5. Then R1 equals 2.99 ohms. And if that's 3, then R2 should be close to 5. So it should be, let's see, 4.99. Yeah, it's 4.99. So in other words, R2, or rather let's substitute it from here. So it's 5 times 2.99 divided by 3. So this answer times 5 divided by 3. Yeah, 4.986. So 4.99 ohms. Okay, so we've got R1, R2, and I guess R3 and R4. Then the last thing that we can work out are the power dissipated by each of the resistors. So the power dissipated by resistor 1, since all right, remember in a parallel circuit, the voltage is the same in a parallel circuit. The voltage here is the same as the voltage there, and the voltage there, and the voltage there. You remember that one, eh? Ricky, we should go to the previous slide so I can illustrate. Remember the parallel circuit we have down here? Yeah, and the voltage is the same there, 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 and there in each of the resistors. Remember that? All right. So because of that, our current is 1,07 in the whole circuit, and I believe, what was our voltage? Our voltage from Ohm's law, we got it to be 6 volts, the total voltage. The total voltage was 6 volts. Now, in the parallel network, the first one, RP1, our power was 2.14 watts. Yeah? 2.14 watts. And we didn't really work out the voltage. So what we can do is, let's see, 2.14. I'm just checking here quick, just to make sure something is, yeah. Okay. So we can use that, to to say, okay, in our parallel configuration 1, parallel circuit 1, what is our voltage? And our voltage is going to be 2.00 volts. And in parallel circuit 2, the power dissipated there was how much? We found it to be 4.28. So 4.28 equals voltage times the current 1,07. And we use this current as 1,07 because it's for the equivalent circuits. It's for the equivalent resistances, sorry. And now that we have got that, here we'll get 4.28 divided by 1,07. And the voltage is 4.00 volts. Ne? And this checks out. So remember when we have connection in series, so between here and there's a voltage drop, and there's also a voltage drop. So in the first parallel configuration, the voltage drop is 2 volts, and in the second one, the voltage drop is 6 volts. But the voltage gets distributed somehow in the parallel configurations, and that's what we're going to work out for each of the resistors, or rather the power dissipated for each of the resistors. And we're going to use the same formula to calculate the power dissipated by each resistor, not the voltage drop, sorry. Yeah. So for each resistor, R1, we will have the power equal, we know the voltage that passes through the parallel configuration, and we know the resistance. Then for R2, we also do the same. For R2, we also do the same. For R3, we also do the same. And again for R4, we also do the same. So the voltage in the equivalent resistance for the parallel configuration, we know it's 2 volts. So that will be 2 squared. And the resistance R1 was how much? 2.99. And this gives us, so it's 4 divided by 2.99. That gives us 1,72 watts. Yo, so sorry. And then the other one is 2.00, so 2 squared divide by R2 was how much? 4.99. And that gives us 0.8 watts. Then the last one, or the third one rather, The voltage is 4 volts, so we square that, and the resistance is 7 ohms, so that gives us 16 divided by 7, and 6 divided by 7, so that's 2.29 watt. And the last one, the power dissipated there would be, yeah, ask.
More hello, yeah. 2 squared divided by 2,99.
Yeah,
Then 1,72.
yeah, ke 1,72 watts. Or did I get the math right or not?
Neke impilo 1,34.
1,34. Okay, so I'm the one who made a mistake, yeah? So 4 divided by 2.99. You said 1,34, ne?
Yeah.
Yes, that is correct. Well done for spotting that. Well done for spotting that. Okay, and then the last one, give 4 squared over R4 really okay. 8,0 resistance R4, it's 8,03 ohms. So that's gonna be 16 divided by 8.03, and that gives us 1.99 watt. So we can end our class here today. Do you have questions? Yeah, sure.
I don't have any questions. So, can I get a question paper so we can practice and then we can like in another chat?
Okay. Do you mind sharing which question paper that is so that we can discuss it as well?
Eric Inch.
Are you gonna be able to share it more screeny?
Oh, I see I'm phone like the question paper here, but feeling in a school like the previous question.
Oh.
Matrix second. Because Banoko required the question internal resistance.
Internal resistance.
Yeah.
Okay. Okay. Like internal resistance of your battery, ne?
Yeah, because salary that day go to introduce Swazan Avalinako. Because
Okay.
the deputy principal, so or flow question people or Rebona or then Utata Arbuta ones reads about
Oh, okay, okay. It's fine. Just quote me the question paper, year and what. Like all the details, jamo pele ga yona, so that, because I'm also going to upload question papers on Google Classroom for your benefit and other tools that you might find useful. So, but just share it, and then we can I'll think of notes that I can put up on Google Classroom. Yeah.
all right, all right.
Yeah. So just mention it so that I can just write it down here. Okay.
Okay.
Which question paper? From which department, etc.
Go the question or
No, just the cover page. Yeah, like Is it department? Is it trial? Is it what? Those information.
Oh, ayinanto vanoziya pages phela ayina-cover page inothoma ka-questions.
I wanna like more fast page mo bangoleng DOE something something. The year maybe.
Ke bona Mpumalanga.
Okay. Mpumalanga. Yes. Go on. What else have they written there?
Se ba ngola Mpumalanga, se ba ngwale le ngwaga or
Is
day
it?
something. Se ba ngwale selo.
Okay, no, it's fine. It's when it's fine. We'll see what we can do. But I'm also going to put up question papers anyway for your benefit. Yeah.
Okay.
Yeah. So it's fine. We can end here tonight. Thank you for showing up. And happy studying. Enjoy the rest of your evening.
Okay, thank you.
Bye.